Hello everyone, my name is Connor Becknell, and today I'm going to be discussing a YouTube heat exchanger failure that occurred during my internship at Entergy. I was able to work at one of their nuclear facilities up in St. Francisville. It was a pretty good experience because I learned a lot about heat exchangers. I hadn't had taken heat transfer yet before that. So I'll start off with a basic overview of how the nuclear plant was set up, and then I'll dive into what actually happened with the heat exchanger. So the basics are is that the reactor creates heat through nuclear fission, and it will heat up water around the core, causing steam to form. And that will be run through a high pressure turbine followed by two low pressure turbines. Basically, that will be the process that's going to transfer that energy from the steam into electricity to be put out to the grid for homes or other businesses to use. And so after that point, before we can pump it back to a pressure that's useful, we'll need to condense it back down to a saturated liquid. It's significantly easier to pump a liquid than a gas. After that, it's going to go through a heater string. And basically, these heat exchangers are going to step up the temperature back to what is required before it is pumped back into the reactor. And there's a small bleed-off line just after the reactor to regeneratively heat up each of these segments of the heat exchangers. And typically, that is the process for most nuclear plants that are boiling water reactors. In reality, there are two of these strings. I left one out just to kind of simplify the process. So this is the basic form of a shell and tube heat exchanger setup. The left one is not actually a U-tube. I basically gave us that picture just so you can see the process of how it's assembled. You have baffle plates that support the tubes. The tubes are slid into place during manufacturing and are typically welded on the ends to hold them down. This here is an actual U-tube heat exchanger, and you can see that the baffles are different because they don't actually go up to the top and all the way to the bottom in each case. That's because the shell that goes over these tubes has the hot liquid flowing over, and it will go up and down between these baffles. So it's actually a cross-flow heat exchanger. You may have learned about that heat transfer, you may have not. This is used because it has a high efficiency. It can take up a lot less space, and having a string of these really allows the efficiency of the whole plant to be increased. So one of the biggest issues with the design of these heat exchangers is, like before I said, that the end caps are welded, but because of the constraints of trying to weld each of these to the baffles, they're not. There's actually a clearance between these tubes and the support baffles. And because there's space there, that leaves room for wear and tear from vibration because of the high pressure that runs through these systems. So eventually, over time, these baffles will begin to eat away the wall of the tube, and the baffles themselves will actually have some degradation also. Eventually, this will cause the tubes to fail. And then you end up having, instead of having a closed system where the hot and cold liquids don't meet, they're now mixing. And that really affects the overall efficiency of the heat exchanger. And so in the case of the plant that I worked at, they did have a failure through this mode. And I was on a team in which we were tasked to suit up in radiation suits and go grab the pieces that actually broke out of the heat exchanger. It tripped a sensor in a reservoir designed to actually capture these fragments in the first place so they don't go through the core and end up having a radiation leak throughout the facility. So you can actually see that these are two tubes that have completely been severed off inside the heat exchanger, and that is actually the edge of one of those baffle plates. And that was my teammate's hand there, just to give you an idea of how large these pieces really were. I was told by other people that these were actually significantly larger than most debris that is found in these situations. So you might be wondering, how in the world did they know that there was an issue other than these sensors saying there's debris? How do they know it was this? So what happened was the temperature outlet of the heat exchanger, because the cold fluid is the working fluid, that's what needs to be heated up and put back in the reactor. It was about 20 to 30 degrees lower than what it was supposed to be. And it might not seem like a big issue, but the problem is that cold water has a higher density, and that increases the reactivity of the reactor because it's slowing down the neutrons, and you need slow neutrons for fission. Now, their first thing that they try to do is try to rearrange the rods so that the core would continue to heat, but it didn't work. So we had to have an emergency shutdown, like the entire plant was shut down. And when they went back through the data logs, they realized that this outlet temperature was low. And doing a very generalized look, heat transfer look at it, you can see that the outlet temperatures depending on the inlet temperature, the heat transfer to the cold water, the mass flow, and CP. The inlet temperature wasn't changing, and an increase in mass flow in the cold, through the mass sensors they had remained constant. So they knew that there was a decrease in heat transfer to the cold fluid. And typically that happens because of a failure between the tubes and they begin to mix. So the heat transfer to the cold fluid is significantly less than before. The way that you actually fix these failures is significantly more simple than I thought. You basically open up the shell of the heat exchanger and stick these popper plugs into the tubes that have failed. They typically check these by using cameras. And once it's screwed, it actually expands and drives these threads into the outside of the tube and creates a multi-seal layer. And they typically run this fine until too many tubes fail and then it becomes an issue. So just to recap, heat exchangers help control reactivity in nuclear plants. They can fail by vibrational effects. Failure can be captured by thermal loss analysis. And the repair is quite simple to repair the broken tubes by just blocking them. That's it. Any questions?